Okay, so we'll finish chapter 4 today. Very simple. Two very simple concepts that we have to discuss. We talked about the different techniques, Norton and equivalent techniques in the last class. This class, we'll be talking about the maximum power transfer and superposition theorem. Okay, so the idea of maximum power transfer is, let's say this is my load here. Okay, and I'm supplying power to the load using a voltage source. Okay, the voltage source itself has some kind of equivalent resistance, source resistance, or I'm supplying power to this resistance through some black box. Okay, let's say through some black box. Okay, and really my aim would be to get the maximum power out of this black box. I really don't know what is inside this black box. My only attempt is to make sure that this guy delivers the maximum amount of power possible. Let's say maximum amount of power deliverable from that black box. Okay, I want to get as much as I can get out of it. That's the idea. And in order to do that, the simple theorem is that the equivalent resistance should match this guy. Okay, for maximum power to be delivered, our load should match our Thevenin. That's the idea. And then, as some of you pointed out in the last class, it really has to do it has to do with matching impedances when you're connecting an antenna, the load resistance to the antenna resistance, so on and so forth. Okay, often we want to match impedance. Impedance is a general form of resistances. Okay, in a circuit so that we get the maximum possible power transferred to the load. Okay, if we are connecting an audio amplifier, what you want to do is to matching the amplifier resistance to the loudspeaker's resistance. This results in the most sound. Okay, so that's the idea of maximum transfer theorem, power transfer theorem. The idea is really simple. We look at the total power delivered to RL. The total power delivered to RL is I squared times RL. That's I. Okay. That's the amount of current flowing. You see, the amount of current flowing through this is the total voltage applied, VTH, over the sum of the total sum of the resistances. Okay, so that's the current. Okay, I squared times RL. Now from your calculus, you know, when you want to look at the maximum or a minimum of a curve, what you want to do is to find the slope. So you take the derivative of this guy with respect to RL and equate that to 0. Where does the slope become 0? The first order derivative when it becomes 0, that is where you have either a maximum or a minimum. In this case, it's going to be the maximum. Okay, so we do the first order derivative and equate all of that to 0. Equating the first order derivative simply means the numerator goes to 0. Okay, so the direct consequence, the direct result of equating the numerator to 0 is that RTH equals to RL. Okay, that's all there is to it, and we'll solve a couple of problems in order to deliver the maximum power out of this. And what is the maximum amount of power? Well, you can see there are expressions for that. V Thevenin squared over 4RL. That's the maximum amount of power delivered to the R load. Okay, the total power delivered is VTH squared over 2 times RL. That's the total power delivered. Okay, of that, half is delivered, half is dissipated in here, and half of that is dissipated in here under the maximum power transfer condition. Okay, so really you can only get half of the power that is actually being supplied by this voltage source. Half of it is going to drop across, and that's the maximum. The maximum you can get is just half of the power delivered from the voltage source. One half is dropped across the load that you want, and the other half is dropped across the source resistance. Okay, we'll do a couple of problems. We'll really do some simple problems. Okay, VTH squared over 2 times RL is the total power dropped. And this happens when RL equals to R Thevenin. Half of the power is dropped over here and half is dropped over here. Okay, so that's the idea of maximum power transfer. Let's look at the superposition theorem as well, and then we look at examples, one example for each of those. Okay, the idea of superposition is, it's a very powerful technique. It's a very powerful technique in a linear system. Remember, in the very first class, I mentioned that there are certain assumptions that we make in this class. The first one is that our systems are linear. Okay, so when our systems are linear, what we can do is think of a resistance. V is I times R. Okay, if you plot V versus current, okay, it goes up. By linear, what I mean is it is a straight line. The relationship between the slope of that guy is going to be resistance. The slope of that guy is resistance. Okay, by linear, I mean that it is a straight line expression. Okay, also that when you increase, okay, when you increase I by a small amount, okay, so what you can do is the change in V is going to be delta I times R. Okay, so the V2, let me not take that route. Let me keep it in simple terms. The idea is that when we have a linear system, okay, we can apply superposition. Okay, meaning that I can calculate the effect of one input, calculate the effect of the second input independently, and add them together. Okay, so the voltage is I times R. Okay, if the input were to change by a small amount, delta I, okay, the output is going to be V is IR plus delta I times R. Okay, so the V new. Okay, if the input changes, I new changes. So the effect of input changing, two separate inputs, two inputs can be broken down into individual responses. I'll show you in a minute. Okay, let's say, so the application of that guy is when you have two sources. There is one source over there, and there is a second source over there. When there are two independent sources, and you want to evaluate the effect of that on the circuit, the idea of superposition is that I can independently evaluate the response or the behavior of the circuit to one source and the other source independently, then add them up together. Okay, then add them up together. Okay, so for example, I'll show you in this example. Why don't I, let me see if this is a very powerful technique. The total response of a system. So let me go over this. The total response of a system is the sum of all the responses from each independent source applied independently. Okay, so that's the idea of uh, superposition. When there are two sources, that guy and that guy, the idea of superposition is in a linear system, I can find the effect of one source by deactivating the other, then do the exact same thing with the other source by deactivating the first one, then add the two responses. Then I'll get the combined effect. Okay, that is not possible in non-linear systems. It's not possible in non-linear systems. So I'll give you an example. X squared equals to y. Okay, so when x equals to a, this is a non-linear system. Okay, let's say to begin with, the first value of x is a. Okay, then what is the value of y1? A squared. Let's say x2, x changes to b. What's the value of y? B squared. Because there is this condition here. Now, if I were to add x1 plus x2, then the response is not y1 plus y2. Okay, because the response of the system is a plus b the whole square, which is not equals to y1 plus y2. Okay, so it is not possible in a non-linear systems. I cannot simply add two independent um, inputs and then do the exact same thing for the outputs. So the output of non-linear system is not the sum of individual outputs. Okay, but we don't have to worry about that. We are not doing non-linear systems. Even when we talk about non-linear systems, we somehow linearize them by keeping the input small. Okay, but the idea is this: in linear systems, we can do this. Okay, in linear systems, when we add the inputs, the responses of the outputs also add. Okay, so that's the idea. We can separately, independently evaluate both of the inputs and their effects on the circuit and add them up, add their responses. Okay, so this is the idea of superposition. I will come back to work on an example. For now, what we simply want to remember is just this guy. Remember just this guy. Okay, the total response of a system is the sum of all the responses of independent sources that are applied individually in a linear system. Okay, so that when we look at an example problem, that's going to become much more clear. Okay, let's see if I can add a page somewhere at the maximum power transfer. Okay, here. Let's do an example. Maximum power transfer example. Let's see, temp somewhere in here. Okay. For a circuit that looks like this, I'm going to draw this circuit here. And the terminals are A and B. And I'm connecting a load like so, RL. So this guy is RL. This guy is 30 ohms. This is 150 ohms. Terminals are A and B. This is a 360 volt source. So there are two questions in this problem. Find the value of RL so that this results in maximum power being transferred to RL. So that's the first question. And the second question is, what is that maximum power? Okay. So in order to do that, the first thing I'm going to do is to look at this circuit that is connected to terminals A and B. Okay. And see if I can write this as a voltage Thevenin in series with a resistance Thevenin RTH, and then replace the overall circuit with its Thevenin equivalent across A and B. Then I know RL will be equals to RTH if I want the maximum power transferred. So what I'm going to do is to calculate the Thevenin's equivalent of this circuit. Okay, So in order to do the Thevenin's equivalent of the circuit, I first have to find the voltage across the terminals A and B. The voltage across the terminals A and B is the voltage across the 150 ohm resistance, which is simply the voltage division. So V Thevenin equals to 150 over 150 plus 30 times 360. Okay, so that's the voltage division, the amount of voltage drop across the 150 ohms. So that is going to come out to be 300 volts. Okay, now let me find the value of R Thevenin. In order to find R Thevenin, what I have to do is to deactivate this source. Okay, so once I deactivate this source, what I have is 150 ohms in parallel with 30 ohms. Okay, 150 in parallel with 30 ohms. RTH is 150 ohms in parallel with 30 ohms, which is going to come out to be 25 ohms. So the idea is now RTH is 25 ohms. So in order for me to deliver the maximum amount of power from this guy to this load, all I have to do is to pick a value of RL that is exactly equals to R Thevenin. Okay, so when I pick a value of RL equals to 25 ohms, okay, when I pick a value of RL equals to 25 ohms, the maximum amount of power will be delivered. Okay, now in order to calculate the power maximum, this guy, okay, in order to calculate that guy, all I have to do is to the voltage across VAB squared over RL. Okay, but we found that the voltage across this guy, VTH, is 300 volts, right? So that's 300 volts squared over RL. Over 4 RL squared, right? Over 4 RL. Okay, that was the formula that we VTH squared. So this VTH was found to be 300 volts. Okay, so the power, maximum power delivered, if you remember, VTH, the whole squared over 4RL, that is exactly what I am using here, and it comes out to be 900 watts. So the application of maximum power transfer theorem is that this RL is chosen to be equal to RTH, okay, which is 30 in parallel with 150. And that's all there is to maximum power transfer theorem. Okay, let's see if I can do some problem with the superposition theorem. Okay, questions so far, please. Okay, all right, let's continue with the superposition theorem, example of the superposition theorem. Okay, so let's go through the question really quickly. Use superposition. Okay, we are supposed to use superposition. There are a bunch of different ways. We could apply node voltage method. We could apply a mesh current method. Okay, or KCL, KVL at different nodes. Now, what we want to do in this case is to apply superposition. we want to apply superposition to find this value. Okay, plus minus V. What's the value of V? So the idea of superposition is that because this is a linear circuit, as all circuits in this class are, what I'm going to do is to evaluate the value of V prime or V dash just to the input source V, 110 volts. Okay. Then what I'm going to do is to, let me see if I can make some room here. Okay. So the first thing I'm going to do is to find out the value V prime when there is just one of the power sources, voltage source acting. Then I'm going to deactivate the second one. I'm going to find V double prime. Okay, that is the response of the circuit to the current source. Okay, so this guy, I'm going to call this guy as V prime 2. So look at this, I'm going to replace this guy with a short. Just like I replaced this guy, a current source, with an open circuit. Remember, I open circuited these terminals to deactivate the current source. So when I'm calculating the effect of the voltage source, I deactivated the current source. Now I want to calculate the effect of the current source, the 4 ampere source. So I'm going to deactivate a voltage source. So to deactivate a voltage source, I replace it with a short. Okay. So I find V prime or V dash and V double dash. So overall V, I know from superposition is going to be V prime plus V double dash. Okay, so that's my approach when I'm using superposition. So we will start by deactivating the current source. Okay, to find the response due to 110 volt source. So that's the first step. And this second step would be to calculate the value of V double prime. Okay, so this is what I did. The full circuit had a current source, 4 amperes current source here. In order to deactivate this current source in the first step, I open circuited it. When I open circuited it, there is no current flowing through this, so I can simply eliminate that. Now it's easy to find what is the value V prime, okay, across that resistance. What's the value V prime or V dash across that resistance? Okay, across that resistance, well, we start by noticing that there is a series resistance here. So that's that series resistance over there. That is in parallel with this guy. That's this guy over here. So the equivalent resistance of all of this is 5.83. Then it's a matter of finding V prime. In order to find V prime, all I'm doing is applying a voltage division between this guy, which is the equivalent of all of that, and this guy. Okay, that 5 ohm resistance. So the voltage division is 110 volts. That's right there, times the equivalent resistance by the sum of 5 plus that parallel resistance. So that's the idea. The first voltage V prime is simply the voltage division between 5.83 and 5 and 5.83. So the equivalent, that is 5.83. All of that, this guy is 5. The voltage division between the two gives me V prime. Okay, that is step 1. Okay, then there is the step number 2, which is to deactivate. Remember, the step number 2 is to deactivate this voltage source here by replacing it with a shot. Okay, and then calculate the effect of this current source to do V double dash. That's step 2. Okay, once I do that, I notice that this guy, the 5 ohm resistance and the 10 ohm resistance are in parallel. Okay, so I redraw the circuit to show that the 5 ohm and 10 ohm resistances are in parallel, because if you think about it, both of these resistances are tied together at their ends, okay, without any other terminal in between. So we have a parallel combination of that. Then there is the 2 ohm resistance. Okay, there is the 2 ohm resistance. So I'm going to write it as 10 ohms over here. Okay, in series with a 2 ohm resistance. So that's the 2 ohm resistance. And all of that is parallel to the 12 ohm resistance. So once we do this, finding the current through this 10 ohm resistance, I should be able to do the current I double prime times 10 ohms. It will give me the value for V double prime. So that's my plan. And we need to find the current through the 10 ohm resistance. And in order, once we go through the steps, we'll see that this is 0.923 amperes. Okay, the amount of current flowing through this is 0.923 amperes. So when I multiply that by 10 ohms, so the current flowing through this is I double prime is and to account for the proper current directions, I get a value of V double prime equals to negative 9.23 volts. Okay, earlier I got a value of V1 or V prime to be 59.23 volts. So in order to find the overall effect V, all we have to do is add V1 or V dash and V double dash. Once we do that, we get a value for V from superposition. Okay, as you can see, this is not the quickest way. If you were to set up voltage equations, you would have seen the answer much more, much sooner. Okay, let's see something in the chat window. When finding R Thevenin, something in the chat from Tyler, when finding R Thevenin in the previous problem, are the 150 ohm and 30 ohm resistance only considered in parallel because they're acting as if the voltage source is in there when finding RTH? Yes. So once we finish this R Thevenin, once we finish this superposition, let me quickly go back to the problem, the previous problem, and calculating R Thevenin, okay, of this source, and calculating R Thevenin of a voltage source right here. Okay, How do you calculate the R Thevenin of the voltage source? You remember the first step in calculating R Thevenin is to deactivate all independent sources. And the way to deactivate a voltage source is to replace it with a short. Okay. And the way to deactivate a current source is to open circuit it. But in here, I have a voltage source. So in order to deactivate that, so this is the first step in finding R Thevenin. When you want to calculate R Thevenin, the first step you want to do is to deactivate all the independent sources. Deactivate an independent voltage source by replacing it with a short. All right. So other questions, please. So that's all there is to chapter 4. We looked at superposition and we looked at the maximum power transfer theorem. Okay. What I want to do is to, let's see, if you don't have questions at this time, let's take a look at this syllabus. We are ahead of this schedule um, by a day or two, but that's fine. By a day or two, actually, a day and a half, but that's fine. I still want to go ahead and get started with the ideal op-amp, chapter number 5. Okay, that may be that may take a little bit of practice, and it's always good to um, spend a lot of time, as much time as we possibly can, with chapter 5 and 9. So now that we have a bit more time, I want to go to chapter number 5. Okay, let's go to chapter number 5, the operational amplifier, a very, very, very interesting circuit. Okay, it is used as the building block. It is unlike anything you have seen before. Okay, it has 5 terminals and sometimes 6 terminals. So far we looked at a resistance which has only 2 terminals, maybe a capacitance which has 2 terminals, an inductance, 2 terminals as well, a voltage source, 2 terminals, a current source, the same, and even a dependent voltage source, a dependent current source. Okay, so all we have seen so far are circuits or elements with 2 terminals. Okay, but this guy is different in the sense that this is an operational amplifier. This is an amplifier. There are 2 inputs. Okay, and then there is a power supply, positive power supply, and a negative power supply. Sometimes this guy is connected to ground. So this is power supply, positive, and this is power supply, negative. Okay, this is input 1 and input 2. Okay, there are 2 inputs, there is 1 output. Okay, so this is a very, very interesting circuit. Fundamentally, what it does is it looks at the inputs and calculates the difference between them, input 2 minus input 1. Okay, and that guy is amplified to give you some output. V output, the voltage on the output, is an amplified version of the difference between the inputs. Okay, that's all there is to it. And it has some very interesting properties we'll talk about. Okay, we're going to look at the ideal op-amp in this case. Okay, in our class we are going to talk at ideal op-amp. So when you look at the inputs, the difference between the inputs is amplified. Okay, that's all there is to it. It's multiplied by some kind of gain. And that's the name amplifier. And then the no amplifier can function without power supply. So there is positive and negative power supply. And then of course there is the output, the all important output. This is what I care about. Okay, so let's see. I'll come back to showing this in many different forms. Okay, so the idea of this chapter is to introduce an op-amp so as to reinforce circuit analysis tools that we developed so far. Okay, just try not to blindly remember the problems or the formulae. Okay, so this chapter is not about memorizing the results, but it's about using the tool set that we developed so far. Okay, so using the tool set that we developed so far. Okay, the real op-amp. Okay, what is sitting inside an op-amp? Okay, what is sitting inside an op-amp is beyond the scope of this class. There are some capacitances. There may be some MOSFET transistors. There may be some resistances, so on and so forth. Okay, but that's beyond the scope of this class. For the purposes of this class, we'll consider op-amp, okay, as a black box, as a magic box that can do some interesting stuff with the inputs. Okay, that's all we care about, the terminal behavior. Okay, how the op-amp behaves at its terminals. We only care about the terminal behavior. All right, so this is something I mentioned earlier. So there's a positive power supply, there's a negative power supply. There is input one, there is input two. Okay, the difference between the two inputs is amplified. Okay, the difference between the two inputs is amplified. Okay, so we can even name these inputs. The input connected to the negative terminal is called the inverting input. Okay, the input connected to the positive terminal is called the non-inverting input. Okay, so that's an interesting nomenclature. The reason is simple. The output is V, if you call this as V positive, V negative, V positive minus V negative times some amplification factor. Okay, some kind of amplification factor. Okay, so that's the idea of inverting. So because the input applied to the negative terminal appears in the negative subtraction scenario, we call this a non-inverting input. Okay, so there's positive and negative supplies. Okay, of course, when you go to 108, triple E 108, you will actually apply, build circuits out of the op-amp. But for now, it's enough to know that there is the ubiquitous, there is the often used 741 op-amp, okay, with its non-idealities and all. But that's just an example of a real-world op-amp that is used in the labs to build interesting circuits. Okay, the rest is all history. Okay, I leave you to go through the history. Okay, so terminal voltages and currents. So it's not a big deal if you take the time to think about and analyze this circuit. It really is a very, very interesting circuit. We apply a positive voltage. See, this is the symbol for a battery. Okay, this is a battery or the voltage source. Okay, this is a constant voltage source. Okay, there is a negative VCC. There is a This is similar to a voltage source with the negative positive polarity shown here. Okay, so that's the idea. So we have to apply power supplies. Okay, the function of power supplies is not for signals. Okay, these are not signals. They simply provide the operating power necessary to amplify. Okay, what is more interesting, so these are not really interesting. Oftentimes we don't even show them explicitly. Okay, oftentimes we exclude them from my symbol. It's not that they're not there, but definitely we need them 100%, except that there's not a lot of action going on those terminals, so we understand them implicitly. The more interesting terminals are these guys. Okay, the two. Okay, and then I call them with different names at different times. Okay, V positive, that's the voltage between the positive terminal and common node. I'm going to call this common node as ground. Okay, similarly, the V negative is the voltage between Vn and ground as well. Okay, or as the uh, common node. We also have the standard symbol. So like I mentioned, um, output is the difference between the positive and negative terminals times the amplification factor. Okay, so but then there are limits. The outputs can only go as low as the negative power supply and as high as the positive power supply. So think of this as the ceiling. Okay, think of this as the floor. Okay, if we were to um, make a high jump inside your house, you can only go as high as the ceiling. Okay, and if you were to go down, you can only go as low as the floor. Okay, so the ceiling and the floor are set by the ceiling and the floor are set by the power supplies. Okay, the ceiling and the floor are set by the power supplies. Okay, let's see if we can move further along. So here is the idea. The V output can have three regions of operation. Okay, the output can have three regions of operation. And it's better understood. This is a little um, little off from the order that I want to follow. Okay, but that's fine. So the idea is there are three regions of operation. Okay, so here is the idea. I'll give you a very, very simple idea. Okay, let's say this is my input. The difference, this guy is VP minus VN. That's the difference between these two terminals, the input VP and VN. Okay, when the amplification is A, okay, the output is A times the difference between VP minus VN, right? What do you think happens if VP minus VN goes up? Okay, so here is the idea. So the output is going to be an amplified version of the input. So if this is your input, If this is your input, the output is going to be an amplified version of it. Okay, what happens if the gain is increased, or if the amplitude is not the amplitude, but the gain is increased? Okay, so when the value of A is increased, what happens is um, the resulting output becomes much higher. Okay, it can even become much higher. But at some point, what happens is the real ceiling to this is supplied by the power supply VCC, or the negative power supply negative VCC. Okay, so the real output is only going to follow a sine wave up to VCC, and then it will behave like a sine wave only up to negative VCC. Okay, so the idea being the idea that the maximum power and the maximum and the minimum voltages are VCC and negative VCC. This is the ceiling I was talking about. It is in the floor. This is the floor I'm talking about. So let me see if I can. So the output, if you think about it, if I clear all of this, the output can have three different values. The output can be in between the ceiling. So this is the ceiling. This is the ceiling. Okay. This is the floor. Okay. So when you're jumping inside your home, you could be in the linear region, so without hitting the floor or without hitting the ceiling, or you could be hitting the floor, that's the saturation, bottom saturation, or you could be hitting the ceiling, that's the plus VCC. Okay, so that's the idea of three regions of operation. Okay, just give me 1 second. All right, so let's continue here. So that's the idea. Here is the three regions of operation. The floor, okay? And this becomes much more apparent when we look at some problems. Then there is the ceiling, and then the linear region of operation about which we care. We want to try to operate in the linear region where we can get the amplification, okay? Where we get the amplification. Okay, gain is actually considered from two views. We'll talk about open loop gain, closed loop gain, all of that, but don't pay too much attention to all of this. We'll come back to this. Okay, we'll come back to this. Let's see. There is another very, very, very important concept that we want to talk about. Okay, when we look at OpAmp, there are three assumptions. When I say an ideal OpAmp, there are three assumptions. Okay, so the three assumptions that I make about an ideal OpAmp are these. Let me highlight this. That ideal OpAmp assumptions, VP is exactly equals to Vn. This is the idea of virtual short in linear mode. Okay. The second idea is that the amount of current flowing in to these terminals, I positive, there is no current flowing in here. Similarly, I negative, there is no current flowing in here. Okay, so that's the idea of the ideal op-amp assumption. I positive, or the current going in to the op-amp positive terminal is equals to the current flowing into the negative terminal is exactly equals to 0. Or this is the idea of infinite input resistance. Okay, this is the idea of infinite input resistance. Okay, two ideas that we use over and over again. The idea is that because of a very, very, very large gain, typically the gain of these op-amp circuits, or the A that I mentioned, is very, very large. Okay, like I mentioned, this is the gain A, right? The gain of an amplifier. There is A times Vp minus Vn. So this is the gain, right? That guy is the gain. So the gain is usually a very large number, 10 to the 4, 10 kilo ohm, 10 kilo, not ohms, 10 kilo or more, 10,000 or 100,000. It's a very large number. Gain is a very large number. Okay. Gain is a very, very large number. Okay. So when we solve problems, so here is the idea of a positive and negative saturation. Um, when the gain is really, really large, or when the input difference is really large, the output is going to saturate at the positive power supply. So the idea is, when you, let's say along the x-axis, you're plotting how much force you're putting into jumping on a trampoline, okay? How hard you're jumping. And then along the y-axis, you're plotting how high you can go, okay? How hard you're jumping. On a trampoline, okay? Along the y-axis, the height, okay? So the way to understand this curve is that as long as you're jumping reasonably hard, as you increase, as you jump with more and more force, you're going to reach higher and higher heights. But at some point, you will be limited by the ceiling. You cannot go any higher than the positive power supply. Okay, that is where you'll begin to saturate. Okay, you can't go any higher, even if you're only going to hurt yourself. Okay, that same thing on the negative side as well. You cannot go any below the negative power supply. Okay, you can only go as low as the floor. So here is the ceiling, here is the floor. So this is called positive saturation, this is called negative saturation, and this is in between is a linear region. It's called a linear region because the relationship between how hard you jump and how high you reach, that's a linear. If you increase, if you jump harder, you're going to reach higher. That's the idea of a linear relationship. Okay, so similarly, if the input is high, the output is high. Okay, this is case one. In case two, if you increase the input, the output is going to be much higher. Okay, if you continue to increase the input, okay, then you're going to hit the ceiling or hit the floor. Okay, so that's the idea of saturation. Okay, so that's the idea of saturation. Three regions of operation for a an operational amplifier. Three regions of operation for an op-amp. Okay, so these are the assumptions that I mentioned, and I'll come back to talk about this over and over and over again. The assumption is that the current going into the positive terminal and the current going into the negative terminal, they're zero, essentially zero. In the ideal case, there is absolutely no current going into the terminals of an operational amplifier. Okay, so the two assumptions that we make, one is called a Watchword shot. The idea of a Watchword shot is any voltage that is applied on the positive terminal or the negative terminal appears across the other. Okay, if I apply a voltage Vn over here, okay, that Vn also shows up magically across Vp. Okay, it's as if these two terminals are shorted. They're not really shorted, they're virtually shorted. They're not really combined, but they're virtually combined, virtually tied together or shorted. And that's the idea of the virtual short. Okay, and then the other assumption is, of course, that the open loop gain is so high, typically in the range of 10 to the 4, that we assume it to be close to infinity. Okay, the ideal assumption, there are rules that we follow when we are dealing with ideal OpAmps. Okay, the non-idealities are beyond the scope of this class, but the idea is that an ideal